All right. Well, um, thank you very much for the introduction. I'm sure it was very nice. Um, and I'm glad we figured all this out. So it's a real honor to be able to talk to you all today. I'll just prefix this by saying that this was work that I done while I was a student at MIT with Adam, and that I'm interested in continuing once I move to EPFL, which is where I will be a professor next year. But it's completely disconnected from what I do at my current employer, Amazon AWS. So with that out of the way, this talk is about literate programming and CoQ tools, but let me actually take a step back and give you a bit of context. You see, at heart, I'm a programmer, and there's nothing that gives me more joy than building stuff. And I find that the best motivation for building something is needing something. So back in the day, when I was in high school, actually, needing something meant building backup software and software to download album covers for my MP3 player. Later on, when I didn't get enough sleep because I spent too much time building tools, it meant building alarm clock software to wake me up in the morning. And this was back in the days where MP3 players were separate things from phones and you carried them. And it actually makes me feel really old now to realize that there's a generation of people who grew up without this separation between your phone and the thing that plays music. So back in the day, I programmed my MP3 player to wake up at a certain time and start playing music. That was incidentally one of the first few times that I was writing real C code. And spoiler, C is hard. So back in the day, I didn't usually go to bed before midnight. So it took me surprisingly long, I think over a month, to realize that if you programmed the alarm for the next day, it just didn't ring at all. Um, and the bug fix that you see is my understated way of saying this alarm clock is completely broken. Um, I'd love to say that this is my origin story for doing formal verification and proofs, but I actually did not come into contact with the Coq proof assistant until about 3 years later. Since then, I've mostly been a systems and compilers person, but amusingly, most of my interactions with my community, the CoQ community, still revolve around tools, and specifically tools for the CoQ Proof Assistant. Early on, it was Company CoQ, this Emacs plugin to make programming in CoQ a bit more pleasant. And then it was revamping CoQ's reference manual. And then it was Alectryon, the subject of this talk. And in the meantime, there was a bunch of other tools. So why am I telling you about all these tools then? Well, you see, the common thread here is that all these tools started from a place of having an itch to scratch, a need to fulfill, and then sharing the result with other people. It turns out that in most cases, if you have an itch, then many other people have that same itch. And what this means is that there are very few itches that are not worth your time to scratch, which is great because boy, are there itches to scratch in the world of proof assistance. So it's kind of funny. If your language has very limited tools, then the only people who come and use it are those who don't need or care about fancy tools. And so you end up selecting just the people who are good enough to survive with limited tools. And then surprisingly, it turns out that people who don't need tools also don't write tools. So rinse, repeat this process, and you get to where we are now. There's a popular XKCD comic from right around the time I started my PhD. And here's what it says. It shows you at the top how often you do a certain task, and on the side, how much time you expect to save on that task. And then it tells you how much you can afford to spend at most on that task before you spend more time automating than you actually saved. So for example, what this says is if there's a task you do weekly and you can shave 30 seconds off of it by automating it, then you should spend at least, at most, 2 hours on this automation process. Otherwise, you'll have spent more time overall automating it than you would have saved. And this is all well and good if you're working in a vacuum. But there's something misleading about this coming. It says you everywhere. So the calculation assumes that you're pitching your time against your time. But if you're writing tools that you share with other people, then all of the work gets leveraged. You get to apply multipliers of tens or hundreds or thousands or even millions of users. And so you get to multiply this top row in the chart on how often you do the task by how often users do the task. And then suddenly, um, everything it becomes much more attractive to spend time on tools. So so for me, that's a strong argument for actually working on tools and working on things that are usable by a large number of people in your community. And if it gets you invited to get a keynote at some point down the line and reminisce about MP3 players, well, what's not to love? Writing tools is just that cool. All right. So what itch are we scratching today? In one word, the itch we're scratching today is proof presentation. Specifically, the presentation of proof scripts in an interactive theorem prover like Coq. Proof presentation, shortly, is everything that has to do with displaying a proof, explaining it to another human being, and sharing it with readers. here's roughly the plan that we're going to follow today. First, I'm going to tell you more about the specific problem that we're trying to solve and how Alectryon solves this problem. Then I'll show you how it works concretely. And I'll take advantage of the fact that I have a bit of time to actually walk you through writing some code. And finally, I'll spend some time outlining an interesting research problem that I'd like to be the next step in this journey. And it's one where I don't have a good answer. I'm hoping that you folks can give me a good answer to it. Traditionally, a math proof looks roughly like what I've shown on the screen. Here, we're proving that in a semigroup with the left identity, left inverses are also right inverses. It's a really cute manipulation. Basically, you assume that for every element in your semigroup, there's a left inverse, so something such that multiplying to the left by that by the inverse gives you the identity, the neutral element of the group. And the proof is basically just reparenthesizing everything and then introducing the right cuts and whatnot. The way this proof is written on the slide is called calculational. And that means that the proof is basically a sequence of equalities with explanations next to each of them. So if you look at the four equalities, they're stacked vertically. Every time, the thing that's to the right of the equality equals the thing that's below it. And then there's a justification for each of the steps to the right. So the reason why we can substitute the EL element by YL times Y is that this is precisely the definition of YL. YL is such that YL times Y equals EL. So we can substitute EL. And then because we know that multiplication is associative, we get to rewrite the expression. And because we know that, this law that they listed here, the productive semigroup element with left inverse is idempotent, tells you that you can substitute the y times y with y here, and this is because of the definition of y, and then eventually you're just back to yl times y, and you're at el, which tells you that el times y is just el by transitivity of equality. And since y was just xl times x, that tells you eventually that xl uh, is in fact the left inverse and not just the right inverse. The right inverse and not just the left inverse. All right. So if you write this proof in Isabelle, which is another proof system that is not Coq, where the proofs look a bit different, the Isabelle proof actually does a pretty decent job of capturing the structure. It's not exactly the same steps in this proof, but it shows the same interleaving of proof rules and proof states. So you have these have, the cuts, the equalities, and then the by justifies the step from the equality. And the three dots signify that we're just repeating the thing that was on the right of the equality before. So we have x times x minus 1 equals 1 times x minus 1. And then this 1 times x minus 1, um, it can be reassociated by the rule that says that um, times is associative. Um, and then we keep going like this, and eventually we have the result that we care about. If you look at the same proof in Coq, though, so if you contrast these two, things look quite different. There's what we want to prove at the top, right? X times x minus 1 equals 1. And then there's QED at the bottom, so that tells us that things are going well. And then there's some unintelligible gibberish in the middle, um, which, if you look at it carefully enough, tells you exactly what's happening in the proof. But it's only a proof script. It's not what we would typically call a proof, especially not in math, right? It doesn't show you the states that the proof goes through. It just gives you an algorithm for deriving those states in the form of tactics. Like here, it's all rewriting, but it could be induction or other tactics as well. So it tells you how to go from the premises to the conclusion, but doesn't show you what's happening as you go from the premises to the conclusion. Um, and there was a fierce debate in the 1980s about exactly what constituted a proof and what the value of a mathematical proof was. And this was the time when people were starting to look into, to spend a lot of time looking into software proofs. And there was a lot of debate on whether these proofs of software had the same value as the proofs for math. Um, and there's a quote, people really used to fight about this. So to exaggerate, basically the point that this paragraph that I'm going to read is making is, who cares whether proofs are correct if they're interesting? Rather, that's the whole paper makes that. But I really love this quote, which is, it's the abstract of the paper, I think. And it says, it is argued that formal verifications of programs, no matter how obtained, will not play the same key role in the development of computer science and software engineering as proofs do in mathematics. Furthermore, the absence of continuity, the inevitability of change, and the complexity of specification of significantly many real programs make the formal verification process difficult to justify and manage. It is felt that ease of formal verification should not dominate program language design. In other words, yeah, don't bother with this verification stuff. Besides, it's not quite as cool as math proofs. And in a sense, there's something valid to this argument. Like proofs about programs can be very dry. And on the contrary, there's something joyful and fascinating about understanding things deeply. And that from a math proof, and that joy is completely disconnected from knowing whether your paper proof covers all the minute details and corner cases correctly. Right? We talk about the big idea, the thing that you understand from the proof, not whether you've done your 15 cases by hand very carefully. But the other extreme is also reasonable, saying we don't care about the proof at all. That other extreme is also reasonable sometimes. Here's an example. It's a theorem that states correctness for a compiler that I wrote not so long ago. It's a simplified version of it. I hope I didn't screw something up while I simplified it for this slide. But basically, it tells you that if you have a program and you interpret it, so those are the original semantics, and then separately you compile it and you interpret the result of compilation, and then you lift the results so that they're comparable between the two. Well, if both are equal, then it means that your compiler is correct. And this is for all quantified on the programs. If you're going to use the compiler, if you're going to be consuming the artifact, this compile function, then does it really matter to you how the 5,000 lines of the Coq proof that actually prove this theorem work? Um, it's there are places that are so automated that even I don't exactly know how it works. In fact, the best part of my job while developing this proof was changing the compiler, changing the definition of this compile function, and having this proof still go through because there was enough automation that things didn't break. So this theorem is really telling me the one thing that I care about, which is the compiler is actually correct. And then we could separately think of whether there's interesting content as to why the compiler is correct. But as a customer, as a client of the compiler, all I care about is that it is correct. Still, not all proofs are like that. Often we're looking to communicate something through a proof. So when we do math, but also when we do education, when we're trying to get people up to speed on Coq, or even when we try to explain to people how a system works, um, we're not just proving things to make sure that they're correct. We're also hoping to share something through the proof. And in Coq, the way we can do this is by running it inside an IDE. So what I've seen on this slide with this animation that I hope works over the internet, but is basically what happens when you execute this proof in CoqIDE. So the expectation is that you're not going to read the proof. You're going to explore the proof using this interactive tool. And this works wonderfully if you have the tools installed in place, right? But sometimes your users don't have the right version of Coq installed. Sometimes your proof has dependencies that are complicated and that take time to compile. Sometimes actually waiting for compilation is going to take too long and people just don't care about it. Sometimes you're reading a paper and you're just trying to follow an argument and you'd like to see the fully formalized version of it, but you're not going to download the code and run it. Sometimes you're on a mobile phone. Sometimes you're just browsing casually. And sometimes you're reading a physical book and that book doesn't support interactively stepping through things. So that's a problem. So what do people do when they have this problem in Coq? Well, basically, the tradition has been until so there was another tool called Provayola, but basically the tradition was you just do something like this. You run the proof in Coq, and then you copy paste the output by hand, step by step. And you could actually, so the funny thing is that Coq has evolved quite a bit over the last few years, and so you could actually simulate most of the style that's done in Isabel, but we typically don't do that. Instead, we just walk through the proof step by step and just copy paste the goals, and you get something that's decently readable. So what we see on the screen is you have the rule, and then it tells you what the goal is, and then you have another step and another goal. The thing that's extremely painful is making sure that these things stay in sync, right? So if you forget to update the comments, then things are going to get really confusing. But here's how it looks in Certified Programming for Dependent Types, a popular Coq book. Here's how it looks in Program and Proofs, which is another popular Coq book. Here's how it looks in Software Foundations when explaining what the print function does. And it's a super cumbersome process. It takes a lot of work. It's easy to make mistake, and it's very easy to forget to update the comments after you change the proof script. And worse, there's no way to check whether the comments are still valid. So you have to rely on readers to point out issues. So if it was ever the case that the function equality x2 function gets renamed and instead get replaced by an alias, then this would remain in place. But then when students run this code, they wouldn't see what's printed here. Um, so there's got to be a better way, and that's actually what Alectryon does. It's two things. It's a compiler that records Coq's output and embeds it within the proof script to create interactive proof visualizations, and separately, it's a literate programming system for CoQ, and I'm going to explain both of these points. So the idea is that instead of having this manually generated thing, we have automatically generated output, where Alectryon has captured what CoQ was producing and then inserted it. So what you're seeing is the same proof, except without the manual annotations. Um, where Alectryon's compiler took the input CoQ file, fed it to CoQ, collected the output, formatted it, generated a web page that interleaves the inputs and the outputs. So each fragment of the original CoQ script is essentially a button that you can hover or click on to show or hide the corresponding proof state, along with any accompanying messages that CoQ might produce. And now every time you make change to the CoQ file, you can rerun Alectryon and it will update the visualizations. And because all the outputs are recorded, browsing through the proof is instantaneous. There's no need to load a copy of CoQ in your browser. There's no need to load large libraries. You're just loading a pre-rendered version of the code. So here's how it looks like on another example where we're doing an inductive proof to prove the Gauss identity that tells you that the sum of 0 through n is n times n plus 1 divided by 2. And yeah, and this has been configured so the file was set up so that some things would be shown by default and others not. So here what happens is that I can expand or collapse parts of the proof. I can hover to reveal those parts of the proof that are not displayed by default. But also, so as a post-processing pass, I can actually change everything to use a different rendering mode. And so here what I'm demonstrating is the same proof, but this time I've used CoQ notations, and I'll say a bit more about how things actually work under the hood here. But I've plugged in a latex renderer, MathJax, to render the same equations in a way that's more familiar to someone who does math rather than CoQ proofs. All right, and here's another example of what happens here. So what we're looking at here is trying to explain to students or to users what it means to construct a proof. So here what we're looking at is we're looking at the result of step-by-step constructing a proof. So now the little bubbles are not showing anymore the output of CoQ. Instead, they are showing the output of a command that's hidden that shows the underlying proof term. So the process of constructing a proof in CoQ is really constructing a proof term. And here, the proof term we're constructing is basically being displayed step by step. All right. So, sorry. Yeah. So let me go back here. All right. So this solves the problem of displaying goals and outputs to readers. But that's just one part of writing a document that includes CoQ proofs. The other part is writing the explanatory prose that accompanies the proofs. In fact, if you inspect this example from CPDT closely, you'll notice that there's no actual code being executed here. It's all prose and comments. And there's a lot of prose around the code. In fact, there's a whole book in there that's written within source code comments. And I mean, this goes back to what I was saying early on, right? It takes a certain amount of grit and determination and passion to make a career out of writing CoQ proofs. And as a result, we have people that are very, very, very patient with their tools writing CoQ proofs. And as a result, we have people who don't complain when they find themselves having to write an entire book out of source code comments. Um, I'm a much less patient person, so I tried writing like 2 blog posts like this, and then I gave up and wrote the tool for it. Um, but yeah, kudos to the people who manage this. So especially because so my text editor has plenty of cool features that let me edit markdown or restructure text documents, right? It has smart navigation, it has spell checking, it has live previews, has convenient shortcuts, and it's particularly frustrating when I end up having to write all my code instead of all my prose instead of CoQ comments because I lose access to all these features. Um, I could try to augment Proof General, the mode I use to edit CoQ proofs, to make it aware of markdown or restructured text, which is this other like markup language. Or I could try to make my restructured text or markdown mode CoQ aware. But the problem is that Proof General is a really complicated piece of software. Generally, it's a very complicated problem to have multiple views of the same document that you're editing in a way that works uh, reliably. Um, so Alectryon's answer is very different. Instead, it's basically a literate programming toolkit. So the idea is, so the code you're looking at on the screen is a snippet from a blog post that I wrote recently. So when you give Alectryon a CoQ file, it can compile it to a web page, but it can also generate a restructured text file by partitioning the Coq sources into a sequence of code and comment blocks, then extracting the comments, and then mapping each code fragment into a restructured text code block. So the idea is that we just flip what is a comment and what is code. So what we're looking at now is Coq code, but there are special comment delimiters that say, hey, this is actually prose. And so then with just one command in my ID, I can flip things around so that now I have a valid restructured text file. And similarly, Alectryon also supports taking a markdown file and then generating a rendered version of it with Coq. So the syntax that you see here is restructured text, which is a cool markup language with a fairly robust story for writing extensions. And in fact, this whole talk is written as just one large Coq file, which I used Alectryon to convert to restructured text and to a web page. And the best part is that you can toggle in both directions, right? So you can either convert from your Coq code to restructured text or back. And so at any point, when you're hacking on the proofs, you have an environment that's perfectly adapted to writing proofs. And when you're writing prose, you have an environment that's perfectly adequate for writing prose. Um, and these two transformations are inverse of each other, so it's easy to switch between the two. I'll give a short demo of how this works concretely in Emacs. It would be super easy to do it in another editor as well. Um, Yeah, so let's see. If you're familiar with literate programming, you might notice that this is a bit different from the usual process. So if you're familiar with systems like web or org mode, where there's really a plethora of these systems, normally you have one main document. And from that, which is neither really code nor really prose, it's really this mix. And from that, you can generate two separate things. You can tangle to get executable source code, or you can weave to get a document that's ready for typesetting or for displaying, so LaTeX or HTML. Um, but generally speaking, the problem with these systems is that because the code is generated from the original document, all the tools that you're used to using on code stop working, right? So your debugger is going to step you through the generated version of the code, not the original document that you actually wrote. Um, your stack traces are going to be in terms of the generated code, not the original code that you wrote. For regular programming, it doesn't matter that much. But in the case of a Coq proof, you need to write your Coq proof to be able to step through things. And what that means is that you can't afford to have a tool that generates Coq code on one side, generates LaTeX on the other side, and then asks you, well, okay, write more Coq code in a setting that doesn't support interacting with a Coq proof. Um, and so that kind of forces you to adapt this mode where the Coq document is the primary one, and then the prose is in comments. Um, and what Alectryon allows you to do is it allows you to break this conundrum by saying, well, there's no main document. You can just translate in both directions. So there's no preferred view. You can pick either restructured text as the primary or Coq as the primary, and store and distribute either of those. If you're writing a library, of course, you tend to a Coq library. You tend to just distribute the Coq source files. If you're writing a book, you'd probably distribute restructured text or markdown. But really, they're convertible. Um, and let me now that I've told you how this works, let me try to hint a bit at what more we can do. And particularly, I'm interested in seeing now that we have this facility, now that we have this rich rendering scheme, what can we do to make things even more comprehensible, right? So step one was how can I record proofs? Step two is what can I do now that I have these proof objects that I can show this output that I can show to the users. So this example, and I've shown this in the past to a number of people, but this example, I have red black trees in the, I wouldn't forget if it's in the Coq standard library or in a separate library, but anyway. And I'm trying to see what happens when I add elements to a tree. And Coq shows me um, what's going on in those trees. So build trees is just going to add one element, then show the tree, then add another element, then show the tree again, and so on and so forth. And what's going to happen is this output is not super readable, but we can define a post processor that's going to translate this into something that we can understand much better. So what we're looking at here is the same data, but just rendered differently. And hopefully that makes it much more clear what the structure of the trees is. But the way it works is uh, it's a hack, and I'll show more of those hacks. But it's a hack. The way it works is it uh, it reparses the output of Coq, and then it translates it into the input of a graph library that is implemented in JavaScript, and then it displays that. So that's in the browser. Another thing you can do is you can do post-processing before even getting to the browser. So what I've done here is I have some compiler that's produced some ELF file that contains as a sequence of bytes in Coq. And I would like to see concretely what this program is. And so what I do is I take this list of bytes, I dump it to a file, then I run the objdump binary to get an assembly listing. And then I highlight the result of that using the pigments library for assembly. And then I inline the result back into the HTML output. And so what that allows me is to treat the output of Coq not as text, but as this richer object. Um, and so here's one last example of this. I have this definition of a glider, which is just a list of lists, right? And then I iterate these definitions, and that allows me to progressively show what's happening in visual terms. Completely the opposite to that, though, but is also a different kind of rendering, is once I started asking myself, well, I'm trying to communicate about proofs, right? So what are the settings I'm going to be writing about proofs? And at first you think, okay, the browser is cool because it has all these fancy rendering schema. And then you realize, well, there's a lot of people who read stuff through RSS feeds, through email deliveries and stuff. Those are much more limited in terms of what they can display. So the way Alectryon works is designed so that it produces something that's readable even in a setting where you don't even have CSS nor JavaScript. You just have plain HTML and it displays as is shown on the slide. So you still get something that's pretty decently readable. I don't want to get too deep into, or at all really, into how Alectryon is implemented, but I'll point out one thing, and it's that Alectryon is smart enough to decouple your prose from your code and to cache the results of running the code. And what that means is that you get a stable archive uh, as the cache of your proof of what's happening in your proof. And so I'll take an example of how this is useful. Suppose I'm in Coq 8.4 and I have some place where I'm teaching the students what the print command does, and I've run the command print plus. And so what that returns is it printed the definition of plus. But then sometime between 8.4 and 8. I think we're at 14, 15, 16 now. Anyway, um, plus was changed. Instead of being a definition directly, it became a notation for nat.add. And so if you're not careful, well, you won't update your proof. And so either the result will be inconsistent with what's written. Well, sorry, not either. It will always be inconsistent with what's written. What this tells you here is it regenerated the outputs. And by comparing the caches before and after, it tells you, well, yeah, something has changed in the output that Coq produces. So it allows you to track very precisely what's happening. And this is particularly important when you have something the scale of the Coq manual, where we have plenty of examples, and then we make a change in Coq, and we don't, without this, we don't have a systematic way of testing were there any unexpected changes to the output. So the manual is full of examples. We can't afford to just recheck them manually, all of them. So this allows you to check automatically. All right, I'm going to give a very short demo. I'll make it a bit shorter than I planned to make sure that we have time for discussing the last thing I wanted to talk about. Let me pull the demo itself. All right, I'm going to stop sharing and then I'm going to reshare my screen, but this time with Emacs. So share screen. I think I can share my entire screen. Share. Yep. All right, so hopefully you should see an Emacs buffer now. Can I have a confirmation that we're seeing an Emacs buffer right now from someone? Ideally spoken, because I can't see anything else.
Might even be yours.
Oh, beautiful. Super. Thanks. All right. So I've opened a Coq file. And what I'm going to do is I'm going to type a very simple proof, and then we'll see how I use Alectryon to render it. So here's this. I'm going to write a silly lemma. I'll call it lemma times 2. And we're just going to prove that for all x, and this is going to be inferred as for all x being a net. If x is greater than 0, then x plus x is equals 2 times x. And if you're following closely, if you're following closely, you'll notice this x greater than 0 is not necessary, but bear with me for a moment. All right, so how does this proof work? Well, this is a typical Coq proof, right? So nothing too exciting about it. In rows, we get 2 hypotheses, and then reflexivity should solve it, except it doesn't quite solve it because, well, 2 times x doesn't unify with x plus x. So why is that? Well, we'll just record the fact that reflexivity fails at this point. Maybe we'll add a little comment about this that says, hey, reflexivity doesn't work here. And then, well, we'll try something else. We'll unfold times. And that tells us that, well, It's that we have an x plus 0 and that doesn't unify. So how about we search for x plus 0? Um, and so, oops, what did I mean to? Oh yeah, and so I don't have a lemma for this, so I need to add a require import arith, hopefully. Take care of that. All right, and so now we search x plus 0 again, and no, why is it not finding a lemma for me? Well, it's fine. I know that. No, it's not fine. Oh, because I want x plus 0 equals 0, x equals x. That's why. Still not. X equals x plus 0, maybe? X equals x plus 0. Well, it's fine because I know that this thing is called nat.add0r, so I'll just rewrite nat.add0r. Not entirely sure why I didn't find it, but that's fine. And then I'll complete my proof for flexibility. Right. I'm happy with this, and now I'd like to share this proof maybe with someone who's never used Coq or with someone who's not familiar with this advanced style of proving important properties. And so I'll open a shell, and I will write Alectryon simple.v. Oh, I need to save my file. That would work better. Okay. And then, oh, and then it's not happy because I did something wrong. So, I did it wrong. All right. Let me try to understand what I did wrong. Sorry. Of course, demos are always like that. They never go the way you want them to go. All right. And also, it seems that my old computer. All right. Well, so okay, we have okay. So this compiles. So now I can open the file. Except my computer is very slow because I'm also on AirMeet, but that's fine. I'm going to open simple.html, and then we're going to see what we generated. Okay, so we have this file now, and we can see that there are various little bits here that we can click on, and we can see how the proof is going through. And in fact, I can change the style that of rendering that is used. So I can have a windowed style that's very reminiscent of what is typically used in Proof General, a CoqIDE, where I can just step through the proof step by step and see what's happening. And that doesn't require running Coq, right? All of this is pre-recorded. So the next step of this is to add little annotations to the proof to say, well, okay, here, for example, for this fail reflexivity, I was not actually interested in seeing the goal again. So I only care about um, the error message. So I'm going to say, hey, Alectryon, don't display goals. And by the way, this fails. So display it with a special little rendering. And in fact, I would like by default to unfold this. So I'd like to show the whole proof as unfolded. So what I'm going to do is I'm going to write a little header that says, hey, for the rest of this proof, let's just unfold everything. Oops. Right. And now that I've made these two changes, I'm going to regenerate the web page and go back to my browser. And if I refresh, now what I have is, well, everything is unfolded by default. The part that fails has this little red underline now, and it only shows the error message. But this is still too verbose, right? Because we have this proof at every stage. Here we're just repeating things because proof says the same thing as lemma. So I'm going to go back and customize a bit more. Here, even though I say unfold for everything, for this one I want to fold. So I'll hide that one. And also I realized at this point that it's a bit heavy to be repeating this h every time because we don't really use it in the proof. So how about we hide it? So I'm going to use, there's a little mini language, a DSL, for specifying what should be visible or not. So what I'm going to say is I'm going to say, well, we're going to hide hypotheses that are named h, right? So what this little directive says is the minus means hide, and then the .h means hypothesis, and sharp means the name. And so the hypothesis named h. Or actually, let's start with, we'll start by hiding x rather. So I'll regenerate, and I will go back to my browser. Oops, sorry, my browser. And here now we only have h left, but we also want to hide h actually. So I'm going to make a similar change, but rather than hiding my name, I'm going to hide by contents because it's not very clean to hide a hypothesis, to rely on the auto-generated name. So I'm going to say, hey, find me any hypothesis that says x greater than 0 and hide that. Except that the very first time that we show this hypothesis, right after the intros, I'd like to still show it. So here I'll reintroduce this hypothesis by reversing basically and saying, hey, I actually want to show this hypothesis in this case. So I save, I regenerate, and I can go back to my file. And what do we see? Well, h is here, x is completely gone, and then h is gone from the rest. And the last thing I want to show in this short demo is, for now I've been treating this as purely a Coq file. But actually, if I start wanting to say explain a bit what's going on in this proof, what I might decide to do is start writing some restructured text, some commentary around this. So what I'm going to do is I'm going to press a key binding in my Emacs, um, and what it's done is it's taken my Coq file and it's translated everything to rest. So I have these two Coq fragments, and I can add text around it. So maybe I'm going to add a title that says um, plus versus times, and here I can use the support that my IDE has for automatically formatting restructured text. So I didn't have to cumbersomely place all these like equal signs. Instead, I just get my IDE to generate them. And then here I want to say that I want to explain that well, reflexivity won't cut it. So reflexivity won't do, unfortunately. I save this, and the same deal here. I want to propagate this annotation to the rest here. Perfect. And yeah, and I'm going to do a second thing. I'm going to mention also the fact that I actually want to hide this h. So I'm going to say we're going to hide h. But the problem with this is, again, sorry, if I just say we're going to hide h, then I have the same problem as before, which is I'm depending on this auto-generated name. It would be much better if I could say something like, how about give me the name of that h? So the name of that h was um, in the sentence that said intros, right? So in the sentence that mentioned intros, um, I'm going to look for the hypothesis that mentions h greater than zero, x greater than zero, and then I'm going to take the name of this thing, and that's what I want to insert to quote. And just to make it very clear to the people who are reading this document, I'm also going to embed the name of that to put a little marker next to the hypothesis. So I'm going to use the same pattern, but this time as a reference instead of a quote. So I'm going to write ref here. And it's just a reference to h. All right. I save this, I regenerate, I go back to my browser, and I refresh, and hopefully it's done by now. Yep. And so now it says we're going to hide h, so it automatically captured the name of h here, and it has put a little marker that readers can click to jump to wherever that hypothesis is here. And this is a really powerful way to actually navigate around code and help your readers understand exactly what's going on in a proof. So this is all going to HTML. But now that we've nicely customized our proof to decide what we want to show or not, we can actually ask it to go to LaTeX as well. So if I take Alectryon simple.v and then tell it, actually, I want you to produce simple.tech. And by the way, let's produce CLaTeX because that's nicer. Um, I can just run that command and it's going to produce simple.tech. And then if I run CLaTeX on the result, simple tech, then after a while and some warnings, I get simple.pdf, which is going to be visible anytime soon. Yes. All right. And so we get the same thing where we have little number one that refers to hypothesis number one and the name of the hypothesis, and the proof just exposed in the form of a PDF file. All right, I'm going to stop the demo here. There was one more thing I wanted to show on more advanced customization, but I'll just skip it in the interest of time. And I'll try to step back a bit and tell you a bit
Let you
of
know
more.
that we're allocating 10 extra minutes for your slot because of the late start. So I don't know if that changes your last decision.
Oh, cool. No, but how it doesn't. Because I'm excited to talk about the problem I have that I'm going to talk about, and then we can spend more time discussing.
Okay.
So that works well. But thanks. All right, cool. I'm going to share my screen again. Back to the slides I was showing. Crop tab. I think I want this share. All right, so you should be able to see my screen again. Okay, so back up a bit. Let me try to address what's missing. First, I'd like to broaden our perspective on what documentation is a bit, and second, I'd like to talk to you about a recent development along with a challenge. So, what's documentation really? I'd argue that given a Coq development, there are really three kinds of documentations that we may want, and I call them internal documentation, external documentation, and per object documentation. The first kind, the internal kind, is what I've been showing you right now. Um, this thing that I call internal documentation is what Alectryon was originally developed for. It really means interleaving commentary and code in a way that still lets the reader process everything sequentially. In a sense, it's exhaustive coverage of your code. The intent is that it serves as a prose description of what's happening throughout a document. So it's the kind of document for which you would use this mode of documentation is when you want your reader to be able to essentially reproduce what you were doing, right? So you have a development and you're documenting it down to making sure that the reader can understand everything that's going on. And this mode of operation is the one I use, say, to write parts of my PhD thesis, this talk, and that people have been using for recitations and lectures and teaching. Um, the second kind of documentation is what I call external documentation, is the idea that you have a Coq development that accompanies a mathematical text, but the two live separately. You want them to be closely connected. Um, they're in sync, but maybe you have a nicely typeset version of some definitions. Maybe you have some extra figures and stuff that are not directly in the Coq code. And really, the Coq code is more, it's illustrating concepts, but also providing confidence about the mathematical text. Um, Ideally, what you want to do there is import definitions, proof fragments, and so on from the Coq code into the math document um, to illustrate your points, but you don't want to step in the order that the Coq document is written in, or and so on. So this is the kind of documentation that you use when you want the reader to have a high-level understanding that you couple with specific places where you zoom in. And originally, Alectryon had no support for this at all. But recently, I've had the pleasure of working with Pierre and Carl and Theo on extending Alectryon to support this. And in fact, because the architecture is fairly modular, we're able to just do a small new front end. So what we did is we added markers in the Coq code that say, hey, an interesting snippet begins here and an interesting snippet ends here. Then we process everything with Alectryon, and then we re-embed those snippets into a larger document. Um, in the long run, I'd like to improve Alectryon further, the quoting abilities and cross-referencing facilities to make this even easier. The third kind of documentation, which I call per object documentation, is the programmer's view of the system. It's not intended to tell a story. It's not intended to pull multiple objects together. Instead, it's an exploded view of your code base that documents each object one at a time. I don't have a story about this in Electron at the moment at all, short of documenting objects separately from their definitions. And in fact, the separation between the definition of the object and its documentation is what we do in the reference manual in Coq. We have a little restructured text construct for every tactic and every error message and every grammar pattern. But there's no direct connection between, except there's a bit of auto generation now for grammar patterns, and that's actually really cool. But for the rest, there's no direct connection. What would be really nice to do is to have a doc string attached to a tactic or to a function, and then as part of this documentation that you're writing, you could pull the relevant bits and embed them, right? Um, so ideally, to make things concrete, I'd like you to be able to write something like this quote, where you say, "Hey, go to the module that's called Coq lists list, and then look for the definition that's called app inch tail, and then in the sentence that talks about induction, pull the second goal out of there." Um, and basically the second half of this notation exists, the first half doesn't exist, and that's what I'd like us to work on. And similarly, you could say, well, hey, actually I want a range. I want everything from the induction to the first auto in that proof of app inch tail in this Coq list module. um, so that, yeah, I'd like to see much better integration of these per object documentation, but also support for these external documentation through Alectryon. And I'm looking for collaborators to work on these aspects. And yeah, I think it would be really great to get to the point where we can have these three working nicely together so that we have uh, individual little documentation pieces for each of the small parts, but then long documents that exemplify how to use things, and also clear documentation of individual source files. All right, so that was one angle. The second angle I want to touch on is these rendering stuff that I showed briefly. Um, I've given a few demos already of special rendering, but let me walk you through a different example. Um, Here's a separation logic formula. So the way you read this, it captures the way some objects are laid out in memory. And the way you read this is you say, well, f2 is a number, a pointer, and it points to the value cell. And cell is a predicate. um, that tells you how a particular bit of memory is laid out. And it says, well, there's this little bit of memory that lives at address F2. And then at address P1, there's a queue. And then at address P2, there's another queue. And then at address B1, there's another cell. And then at address C2, there's a segment of a list, which means just a portion of a list. Um, and um, and well, you're supposed to make sense out of this. An alternative representation of the exact same thing is this graph. And I hope that we can all agree that this graph is actually much nicer to look at than what we were looking at just previously. Um, and so let me actually give you a quick demo of how this can be made concrete. So I'm going
I
to
don't see
play
the
this here.
graph.
What is it?
I didn't see the graph.
You didn't see the graph? Oh no.
Nope.
Okay, well, it's fine. There's going to be a live demo and you're going to see the graph.
All
How
right.
about that? If you still don't see the graph in 30 seconds, please complain loudly. Share screen and Chrome, and I'm going to share the whole Chrome actually. I think I can do that. Meet, share. All right. So this is a proof that I shamelessly stole from CFML, I think. So kudos to Artur for writing this proof. I don't fully understand what it does. Um, but here. So what we're going to do is on the left, you have, so at this point, you should see some proofy bits. On the left, you have a proof script. On the right, you have the Coq goals that are being shown to you as you step through the proof. And never mind what's written after code. Really, it's pretty systematic to understand what you need to do based on what the head of the code is. What we care about is this little bit in the pre thing. So the pre thing tells you what's the precondition of my code. And then if you scroll all the way down, there's also a post that we're going to establish. But the way we're going to reason is we're going to munch on the code little by little, and we're going to uh, see the impact it has on the precondition of the program. So here it tells us we have two queues, and what we're going to do is we're going to concatenate them into concatenate the second one into the first one, and then the second one will be empty. And so if we step through the proof, it's really symbolic manipulation. So it tells us that we can actually expand the definition of queue, and then we can step through. And it's very clear what's happening here. Basically, we're just like we're seeing that the code is just restructuring the pointers and moving the data pointers around. And progressively, we've constructed exactly what we're looking for. And if you're like me, this is pretty hard to think about. But here's an alternative. This is the same thing, but this time we're looking at a automatically generated rendering of the same thing. So remember, we had a P2 points to a queue called L2, and P1 points to a queue called L1. And Adam, this is your chance to speak if there's no picture showing on the screen right now. But as we step through the proof, we're going to see how the transformation of the precondition translates in terms of a visual representation. So here what this says is, well, a queue is really a cell that points to some list such that the last element of the list is also what is pointed to by the second member of the cell, right? So we have a pointer to the beginning and a pointer to the end, basically. So we have both of these. And as we step through the proof, what the code is going to do is it's going to look at, well, okay, is my second list empty? Because I think it's running a loop, probably. So I'm going to destruct that list. So now I know that my list, yeah, sorry. So here my list is known to be the concatenation of some element and then, oops, sorry, some element and some list. And so that means that really, because of the way the list predicate works, this is one cell followed by another list. And so then we can keep going with the program, and that just cuts things up. And then we keep going. And as we step, um, we're reorganizing things in a way that we reattach the pointers until eventually we have the list that we care about, which is our original list. So yeah, we can just recompactify everything together. Oops. Get everything back together, L1 plus X plus L2 prime, and then the second list is empty. And again, I argue that this is much easier to follow for a normal human being than what we were looking at before. Okay, so how does this thing work? Let me play this little resharing and unsharing game once again. Stop sharing. Um, the short story is it's a complete hack. It's not at all satisfactory in terms of the way it works. And the reason why not is that what it does under the hood, sorry, is yeah. So what it does under the hood is um, let me try, sorry, to get things to update. Wait, wait, that's frozen. One second. And yes, refresh. Come on. Sorry. Okay. Um, Sorry, back to where we were. So, um, complete hack. It's a complete hack because I designed the example in a way that makes it possible, but there are two problems. First, the connection with Coq is terrible. So the way the connection with Coq works is I've made some notations that are relatively easy to parse. Then I defined a grammar for these notations. Then I have a JavaScript parser that parses this. Then there's this phase of graph analysis that just does a clustering so that we see the independent graphs. And then there's a phase that munges things so that the graphs remain relatively stable. And then I feed this, of all things, into a version of GraphViz, the graph visualization software that was developed at AT&T in the 80s or 70s, maybe, I don't know. Compiled to JavaScript because that's the only decent graph library that I found that could support this. And yeah, that's it. So it really doesn't scale. So the question is, how do we do this right? And the way we do it right is two things. First, we need a notion of alternative notation domains. We need to allow users to define their own notations in a way where they extend Coq's notation system to support something that's going to be used for printing in specific contexts. So you want to map your Coq code not just to text, but to pictures, to latex, and so on and so forth. And conveniently, because the notations are not reparsable, you don't have to pass the entire AST to a tactic that you don't have you don't have to have a purely text-based version of it. So we don't have to piggyback on the existing notation mechanism. You can just pass the entire AST to a tactic, and then that tactic is responsible for producing another AST and a domain-specific language of renderings. And so what we need then is domain-specific languages for those renderings. So graphs, latex math, pre-printed text, syntax hiding, and so on. And the Lean folks actually already do some of this. There's really cool work on what they call widgets that let you basically map arbitrary Lean structures, Lean objects to HTML. Um, the problem I see with this is it puts too much responsibility on the programmer, and that will become clear when I walk you through the challenges there. There are many, many challenges in here. The first is that it requires continuous solutions. So you saw when I was stepping through this separation logic proof, as much as possible, I tried to make it so that things would stay in place, so that nodes wouldn't just like jump around. But when you think of most, say, graph placement libraries, there's a chunk of randomness that is used to actually optimize the placement, right? So there's a metric that it's trying to optimize for, and then it just randomizes through a bunch of seeds to see which one leads to the best layout. But if you're trying to step through a proof, this is a catastrophe because now what that means is you're stepping and stepping and stepping, and everything looks completely different from one step to the next. And the worst part is that you can't even optimize. So if you're doing this purely in the context of Alectryon, then you can optimize by saying, okay, I have the whole proof. So what's a layout that's going to be relatively stable across all the steps of the proof? But if you're in the context of your proof assistant, the proof is not even finished yet. So you don't even get to say, I'm going to do a global optimization problem. You have to make a best guess at the first step, and then as much as possible try to stick to that. So you need a graph placement strategy, a node placement strategy that uses as a very strong prior the solution ahead for the previous step, which also means you need to be able to match subparts of a goal to parts of the goal that it was just as it was previously. The second thing.
Clement, I just want to
Yeah.
jump in here and say we're hoping to leave 10 minutes of break, and therefore this is probably a good time to switch to taking questions.
Yep, I
If-
have two more sentences and then I have questions.
all right,
So
great.
yeah, perfect. All right, so the second place in which things get hairy is when you start having multiple domains, right? You saw briefly there was a list concatenation within one of those nodes. Imagine if there was a large piece of Coq code inside of one of those graph nodes, right? So now the Coq code, it could be essentially arbitrarily wide or arbitrarily tall. It depends on how you configure the 3D printer. And then the graph can be laid out differently depending on what size the nodes have, right? So you have this joint optimization problem on the graph layout and the parameters that you pass to the 3D printer for Coq code that's inside the graph. Um, and the third problem is we're hoping that this is going to work for static displays, right? So we can't afford to just say, well, we'll just have a generic representation and the user will just explore it interactively because we're hoping that this will work also on text. Um, and finally, there's the problem of editing this stuff. But here, my current thinking is that we can cheat a bit because it turns out that in most cases, the display structure and the text structure, they kind of match. And so it turns out that you can just essentially make it so that when the user clicks on a subpart of the structure, you just give them the sub portion of the text that corresponds to that to edit. So I think this we can get around, but the rest is much more tricky. All right, and that's what I'm going to leave you with. I've shown some of the related work on this slide because everything that I've presented here exists thanks to almost a century of efforts and reflection. So to recap, Alectryon provides an architecture to record and visualize Coq proofs, which facilitates sharing and interactive exploration of proof scripts, and a bidirectional translator between woven and tangled documents that enables seamless editing of prose and code. the next step is to invest in rendering. So please come talk to me if you're curious about these issues. And by come talk to me, I mean virtually, because I'm not actually at CoqPL in person, at CoqPL in person. But if you're curious about these issues, I'd love to chat. Um, and let's use the few minutes that we have to discuss everything that I missed. Um, Thanks so much. Thank you.
Thank you, Clement. Okay, yeah, it's probably better for you to stop screen sharing, and I'm going to make some questions appear in AirMeet.
All right, beautiful. I will stop presenting.
Here's a top ranked question. You showed us a bunch of tools that produce great results, but there's some setup involved. What's the easy on ramp to gradually adding this into projects?
Yeah, so it's a great question. Um, as much as possible, I've made it so that for fairly simple builds, Alectryon can be substituted for CoqC. So if you have a command line that works for CoqC with -q, -r, and then your file, then just plugging Alectryon in there instead of CoqC is going to generate an HTML version of that file. So the hope was that there's this very smooth on ramp because it has the same command line as CoqC. Um, my dream, but I haven't had time to do this, is to do the trick that the WebAssembly people do, where you actually use system call tracking to actually interrupt every call to CoqC and then swap them out dynamically when the make file is running. So you run make and then magically it would generate everything, but we're not there yet. But all these features are layered really. So when you get started, um, you just do the very basic thing, which is converting a .v file to a .html, and then you build up on top of this progressively.
Okay, thank you. Aha, next question. Show on stage. Gregory wants to know, can we use these while we're in our favorite CoqIDE instead of just after the fact?
Yeah, and I think, and the answer is yeah, of course you would want to do that. And so the way I approached this was, let's make a prototype, convince ourselves that it's nice, and then let's implement it in IDEs. And that's why I push for first order support in Coq for this stuff, is that once we have a well-established language of renderings, then we can plug those into IDEs, right? And Um, we might even have one renderer that all IDs would be able to call. And this way you wouldn't have to be re-implementing this whole rendering layer in every different IDE.
Sounds good. Next most upvoted question coming up. Uh, how can you help us see the hierarchical structure of proof scripts that are written linearly?
Benjamin, you monster, why do you write linear proof scripts? You have bullets. You're not supposed to write linear proof scripts anymore. This is Atom land where proof scripts are linear. Um, yeah, so reconstructing structure is a hard problem. I've been trying to. So one place where you really need this is diffs, for example. So you would like to show at every step of the proof the diff with the previous step of the proof, and it turns out that when you have a fork in your proof, the previous step is not the line right before, it's wherever the fork happened, right? So when you do induction, in the second case of your induction, you want the diff with the state before the induction started, not the state at the last proof step of the previous case in your induction. Coq has this information, although arguably Coq proof is not actually a tree. It's a directed acyclic graph because voice sharing and blah, blah, blah. But I'm pretty convinced that we can actually manage. So I think the hope is a mix of reconstructing some structure, but ideally it should be in the proof to begin with, and then linking together goals so that, for example, when you point your so one thing I'd like to have, and there's actually a feature request, is breadcrumbs, right? So with a goal, you would have a breadcrumb of every proof step that led you here. So you would say, well, okay, there was an induction, and then there was a destruct, and then there was an apply of this theorem, and that's what led here.
All right. So in the interest of allowing the student volunteers to spring into action and try to reconfigure the audio in time for the next session, I'd like to suggest that the room at Popple now decouples from this online experience, but I'll take the one last pending question, and the people who are watching on their own laptops can experience the answer.
Great.
And so
Thanks
that
so much for attending, folks.
question from the two is, basically, must there not be other tools that deal with some of the challenges you told us about? And how much of what you're figuring out here is sort of tackling questions for the first time?
So the nice part about getting to give a keynote instead of a research paper is that you get to ask questions that you don't have the answers to. So that was me doing this. Um, as far as I can tell, it's a slightly different problem setting from what is commonly done. So, for example, the fact that you want continuity in graph renderings, I'm sure someone somewhere has studied it, but it's not a super mainstream thing, right? So Penrose, for example, is this really cool tool at CMU. Um, but the way it's designed to work is it's going to help you generate a visualization, and then you're going to take this visualization and put it in your document and never regenerate it again, right? So the intended, as far as I understand, mode of interacting with it is you click a bunch of times on a button that randomizes, that gives you something that satisfies the set of constraints you've defined, and then eventually you have a picture that you like. But the problem in the context that we're in is that um, there's no particular reason why the seed that has given a good result for step one of your proof is also going to be a good rendering for step two of your proof, right? But I'd love, I mean, Penrose is super cool, right? So if I could connect to that, it would be a bliss. But right now, I think it doesn't completely fulfill the problem I have. Um, for the problem of joint optimization, this is something that's a bit better studied. There's a, although it's funny because so essentially what you'd want is when you have a when you have a piece of text, right? You get to choose the width, and then you run an algorithm that lays out the text within that width, right? So you say 80 columns, please print a term with 80 columns. But in fact, you could look at the function that maps what is the number of lines based on what is the number of columns, right? And so now you have a frontier of realizable things, and you can weigh down those that are very long lines or those that are very short lines, and then you can just plug this family of boxes into an other optimization algorithm that lays out the graphs. But even in terms of graph layout is super hard, and the set of tools that actually do things well is fairly limited, right? In the end, I found myself using this AT&T tool, GraphViz, compiled from C to JavaScript. It's really not fun. It was the like fourth library that I tried, and it's the one that did sufficiently for this separation logic thing. So yeah.
Okay, so I think now we come to the second end of this session. Thank you, Clement. Thanks for all the questions from the audience, and we're going to